Good morning. Today we'll be presenting the Matlab code for the first week of the Electrical Distribution and Networks project. So to start with, we have made this database for the different systems that the students were planning. To classify them, we have used structures, organized lists that can handle different data types. So we can store variables as strings of characters or as numbers, which makes it useful for organizing it. Once we run this program, you can see that the struct is printed out here to console, and it also makes this figure comparing the different uh, electrical installations and their voltage. So we can see here that the industrial facility and the commercial center both operate at 20,000 volts, whilst the residential complex and the commercial center both operate at just 400 volts, which is a huge difference. But we aren't even nearing the high voltage applications. This is still considered medium voltage. After this, we have also made this program to help us select what how we should install the different lines, so we can tell it what voltage the installation is going to run at. So if we tell it that it's going to be at 500 volts, and we say that it will be applied as a main feeder line, so we put 1, and we say that we want it to last for 20 years, it will tell us that it, it will counsel us to use aluminum as it is cost effective, and we only want it to be around for 20 years, so it can easily be replaced. And it recommends a mixed special case. This is the catch-all case. And then it also says that it requires a detailed analysis. So I suppose that main feeder lines aren't usually designed to last only 20 years. So this is a case that requires special attention. Afterwards, we have also designed this pie chart to compare the different conductors and their insulations being used. And we can see that aluminum was found to be justified only for one application, and this is for the medium tension side of the commercial center project, as it is the only application that has high enough power and assumably a long enough line to justify using the composite, the LA type aluminum core steel reinforced composite. Afterwards, we have a similar database, but this time for the conductors. As you can see, we have kept using structs. However, this time we have organized their different electrical, physical, and even economic properties. So once again, it prints it out to console. After this struct, we have created this program to compare the electrical properties. So once we run it, it generates a few figures, and it also gives some more specific facts. We get figures on the progressive installation cost, the power loss, and the voltage drop. Something interesting, and the maximum admissible current. Something interesting to notice that the voltage drop and the power loss look identical. This makes sense since they're proportional, and in both cases we see that the copper performs better, which makes sense as it has the best conductivity. The installation, however, is the exact opposite, with copper being the most expensive and aluminum being the cheapest. However, one must take into account that the longer the installation lasts, copper will actually outperform aluminum in the cost, as it requires less maintenance, and copper wears down faster, even when it is reinforced by steel. The admissible current for the aluminum and the aluminum steel composite is the same, which makes sense as in both cases it is aluminum, the main conductor agent, and because of the skin effect, one can assume that most of the charges are concentrated at the edges of the conductor, so it makes sense that only the aluminum will be conducting and not so much the steel. We have made a similar program for comparing the physical properties of the materials, where something interesting to note is that whilst The aluminum steel composite has the highest tensile strength, which makes sense as steel is a very strong material. It can support up to 1500 megapascals, far more than the copper or the aluminum. Copper actually has the higher Young's modulus, meaning it is more rigid, meaning it might perform better in windy areas or places where you want a conductor that doesn't deform as much or doesn't move as much. We have, for the installation systems, what we have made is a database. However, instead of making charts and graphs, we have made it more information oriented. Of course, we have a bar chart comparing the power capacity, where we see that XLPE can handle about 25% more power than PVC, and it can also operate at higher temperatures, whereas PVC starts to break down at around 70 degrees Celsius. XLPE, you can use it at 90 degrees Celsius as per the law. However, XLPE is more expensive than PVC and more rigid, which makes it harder to install, and it is less recyclable as it is a thermoplastic. PVC, however, does have some combustion byproducts that are highly toxic, so if you do breach those 70 degrees or more and it does start to burn, you are going to get some noxious gases, which are not good for the general public. This is the same program that I showed last time, and this last one is for the basic applications, the basic calculations that were used. So for the resistance, we have applied the formula as it was displayed in the document, and we have just put uh, the values in. Same thing for the power, where we have used the triphasic power formula using the line voltage, and then for the power drop, we have just multiplied the current by the resistance, which gives us the voltage drop per phase in phase voltage. So if you want the line voltage, you would have to multiply by square root of 3. If we run this program, we get a table, which is a much nicer way to display information, showing the different cases that the 3 students had to solve for. We see that the commercial center is the heaviest case with the biggest voltage drop, the greatest resistance, and the highest current. So commercial centers do suck in a lot of power. Thank you for your attention, and I hope to see you in later projects. Good night.